Hello, my name's Alan Folmsby, and today I'll be talking about paramagnetic types of materials. So I already spoke on a previous week about diamagnetic and paramagnetic, but I find really that paramagnetic has two different classes. One having rings of protons and one without rings of protons. Basically, everything uses the protons and electrons in atoms. For example, like here, I made a little model of the hydrogen atom, and it's white proton, brown electron here, separated by three little wires, and they represent the two space-like dimensions in black and the one time-like dimension in red. And I've filled in one of these loops there with the spin, one of the spins of two different spins possible. I think I'll turn on a light. Okay, so here we see just one atom, but if you get a molecule of hydrogen, you're going to have two atoms put together where the red loops come together, making it diamagnetic. And I'll just hold up these two here. So there you can see the two red loops overlapping each other, and makes it two time-like loops, time-like dimensions going together, making it diamagnetic. So paramagnetic is the opposite of that. So it's two space-like dimensions overlap and make bonds, which make elements paramagnetic. So I'm going to be talking about the geometry of different nuclei. And basically iron was the paradigm for all magnetic types of phenomena and apparatus. And iron has two rings of protons, 12, as I've said before. And there are space-like areas and time-like areas in molecules. And this is the flow between that proton-electron pair, which I showed you a minute ago. Now, these space-like areas can be bonding in atoms, or they can go out far from atoms as a field, as in ordinary theories talk about fields going away from material objects and acting on one magnet to another. So now there's two classes of paramagnets that I'm going to be talking about. Those that have rings of protons and those that don't. For example, the ones that don't have rings is lithium and oxygen. And all of these, they're all on the left side of the periodic table, mostly. And paramagnets are on the right side, mostly, of the periodic table. And they sometimes have rings of protons in this class of terbium and dysprosium. So what I'm saying is the paramagnetic elements are on the left side, diamagnetic on the right side of the periodic table. And I have a picture of the table I'm going to show you in a minute for that. And I'm going to bring the camera around here and show you how that looks here. All right, so I'm moving the picture around here a bit. All right, so let's switch over to the camera here. So this is the new periodic table of nuclear structure. So all the columns are the groups and the rows are the periods in the table. And on the right side is lots of diamagnetic elements, and the left side lots of paramagnetic elements. And in fact, I have a specialized picture I'm going to bring up for you, which shows just that. So here on the right is the new picture of the periodic table, and you see on the right is diamagnetic on the 8 columns on the right 8 groups. For most of the elements, it's diamagnetic. And on the left is a blue section, which is the paramagnetic. And also I've shown which ones have 2 rings of protons in the nucleus. So I'm going to zoom in on that here. All right, so here we see the iron, cobalt, nickel group there has 2 rings of protons. Chromium has 2 rings. And then the zirconium, niobium, and molybdenum area has 2 rings of protons in the nucleus. And also the gadolinium group there down near the bottom. From samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, and thallium. And so those all have various paramagnetic or non-paramagnetic, just ferromagnetic at low enough temperatures. So for example, gadolinium, let's see, I have a list here of what the temperatures are there. Okay, let's see. I can't show you the copyrighted material here, but let's see, gadolinium 292 degrees, and then the terbium 222 degrees absolute temperature is where it transitions from ferromagnetic to paramagnetic. And then there's also, let's see. Oh, sorry, I was blocking the picture there. So the point is that if you go to low enough temperature, a lot of these elements circled down there will become ferromagnetic, and above these temperatures of like thallium, 25 degrees absolute, it'll become ferromagnetic below that. Okay, so now I'm going back to the description on the PowerPoint here, in which, as I was showing you, paramagnets with rings of protons, like terbium through dysprosium, and then there's other ones without rings. So I'm going to just show you the model of lithium here. There you have the white protons and brown neutrons there in lithium. No rings there. That would be hard to make rings of protons, as opposed to like iron or zirconium. For example, let's look at the periodic table here for zirconium. Oh, here it is. All right, so this thing is supposed to stay where I put it. There's zirconium with the cube at the center of the nucleus, and then the black protons and neutrons covering the 6 faces of the cube. And I have a video I'm going to show you now of exactly what the 3D model looks like. It's about 3 minutes and 42 seconds or so. zirconium. Over here on the periodic table, we see it's a lot similar to iron. It's just that on the sides there are these larger pyramids. And here's the model of it. It shows there's a loop of white protons, and it's got two of them. And as you take it apart, you see that it has all these larger pyramids on four sides of the cube, and then two small ones on top and bottom of the cube. So that's how it's built, and it's just that the two loops are not coaxial, so it is not ferromagnetic. Back with zirconium again, and the point is that the coaxial shape is important for ferromagnetism, and here I've shown the zirconium nucleus with the 40 white protons and 53 dark neutrons, and I put this axis through it so you can see that there's this, going through the cube, there's these two different toothpicks. Now the coaxial angle would be down a bit lower than that. For example, down like this angle. So you see this toothpick here might be from corner to corner of the cube, but the coaxial angle, or the axial angle of this front loop would be a little lower. So I'll turn this around so you might be able to see it better. Okay, so that showed you some pictures of zirconium and how the charge distribution in the nucleus is set out. But as far as paramagnetism goes, that is paramagnetic as an element. And yet the two rings of protons don't seem to make it any more powerfully paramagnetic than its neighbors, which are not set up so nicely. But here in this new picture, I'm showing you the platinum is in the blue section, the paramagnetic, and the gold right next to it is the diamagnetic section. So the last 8 columns on the right side of the periodic table are mostly diamagnetic, so they are repelled by a magnet. But platinum is attracted by a magnet. If you put a south pole towards platinum, it'll be attracted. But if you put a north pole towards platinum, it'll still be attracted. But gold, with one more proton and a similar nuclear structure, is not such a good catalyst, and it's repelled by a north pole. But then if you take a south pole and point it at gold, it's still repelled because it's diamagnetic. And this is one of the weakest things you can find in these elements. Diamagnetism is like 5 times weaker than paramagnetism. So if you look at the entire periodic table, you see that they're divided into groups, really. That there's paramagnetic on the left, and it's not a simple rule that we can make up. But let's talk about lithium and try to imagine a simple rule for lithium. All right, so here's lithium, and it's on the left. It's drawn with only the space-like dimensions shown, like a little propeller. But on the right, I've drawn lithium with all three dimensions connecting each red electron to each black proton. You see how there's a straight line of 3 black protons on the right, like that lithium model I showed you earlier, and 4 white neutrons there. But each of them is paired up with 1 electron using 2 black space-like dimensions and 1 red time-like dimension. So on the left then I've just erased all the red lines and just left in the space-like. So that's why it's attracted as a vortex of a magnetic field, like an electromagnet or like a iron bar magnet. That vortex comes into the lithium space-like dimensions and sweeps it up. It gathers lithium in, attracting it into the vortex. But the opposite occurs for hydrogen. Diamagnetic, it's the red time-like dimension on the left, which makes that loop, and it goes the opposite direction of space. So the vortex of an iron bar magnet will repel the diamagnetic red ring there, because that's a time-like loop. Paramagnets have the space-like loops, which are attracted by a vortex of an iron bar magnet. So you may wonder, as I do, why so many elements are diamagnetic of the same weak value, plus or minus 50% or something. Well, let's take a look at a typical complicated thing like uranium down the bottom row there. The charge distribution here of this model of uranium-234 shows that yellow protons and the gray neutrons in chocolate spheres. Now these were showing that protons form lines of protons, and that's because electrons are free in one dimension and constrained in 2 dimensions by the proton connection, those 2 space-like dimensions there. And yet they're free to go in one direction, and so the protons line up into lines so the free electrons can move around in one dimension. So it's so complicated, you might think, well, why is this paramagnetic and yet californium is diamagnetic, even though it looks almost the same? It just has like 6 more protons than this, and it's based on the uranium foundation. So why does that become diamagnetic for like curium? Just adding 4 more protons to this shape, it goes from paramagnetic to a weak diamagnetic. So I don't have a complete explanation for that. I'm starting to work on the basics here. So now I'll just go back to a PowerPoint slide here and moving along. So these are useful for future research. Consider examples, gadolinium and terbium. These are right next to each other in the periodic table. And gadolinium has a shape which I'm going to show you very soon on the camera. Stand by. And this is going to lead to future research on tolerances and how strong is the near-field electromagnetic electrodynamics here. All right, I'll get out this gadolinium model here. Okay, I've just brought out gadolinium model with the green protons and the white neutrons. So this ferromagnetic at room temperature, shaped like iron, 2 rings of green protons and the white neutrons. But instead of at the center having one axis proton, you see there's 2. And that's good for its ferromagnetic attributes because that stretches the field, and its 4-layer pyramid here is stretching it vertically in the up direction here. And the smaller pyramids on the sides have 3 layers. And that stretching then allows this element to be ferromagnetic, but terbium is not because it's got 1 more proton added on this pit here. So by making it have this little defect in the coaxial nature of it, it changes at room temperature from ferromagnetic to its paramagnetic, unless you go below 222 degrees Kelvin. And then the heavier elements is add more and more protons onto this axis area, making it worse shape and less like iron. Iron is the ideal shape for a magnetic apparatus, and the more protons you add in the center here, the farther away from perfection it becomes. And now these tolerances can now be used to the advantage of modern science of the future, where the temperature dependence of geometries here will tell us how these fields are working. Those 3 dimensions I pointed out. What are the strengths and all the properties of that, and how that affects quantum mechanics. So in other words, by now knowing the shape of the nucleus and its charge distribution, we can use these facts about paramagnetism to calculate the fundamental physics of all matter. And I propose that there's 8 dimensions that should be accounted for. The usual 4 for gravity, X, Y, Z, and T, and 4 more, 3 of which are space-like. And this makes up a conveyor belt of the wave function. The electron gets 2 dimensions. I call them Hx and Hy, and the neutron gets 1 dimension called Hz. Going the other way from the electron to the proton is a time-like reverse belt. And so it's a conveyor belt where it goes both ways. The top side does the work, and then there's a hidden away side, magnet time, which is the sum of Hx and Hy. And Hx is a velocity. And if the proton's moving around at a different velocity than the electron, then Hx gets that extra velocity, which goes to the electron. And that's creating ferromagnetism and all kinds of magnetism for even copper coils. So here's that periodic table I was showing you earlier on. The paramagnetic ones are on the left side with dim blue circles around the elements. And down in the middle, you see the purple area where there's 2 rings on all those heavy elements down there. Those are all paramagnetic at temperatures above the Curie point. And yet below them, below the Curie point, they're ferromagnetic. At least some of them are. Gadolinium through thallium. And then in conclusion, I just wanted to point out that there's 2 types of paramagnetics elements. Lithium class of paramagnet and the terbium class of paramagnet. And you can get more links for things at the pyramidal cube. So thanks a lot for watching today. Bye.